Let's now consider how we can train a linear network. So first of all, remember when we're using a linear network to generate an output, what we do is we present a data vector, or it could be a sequence of them, but we present a data vector and then we basically weight each individual element by the corresponding weight in the matrix, a weight matrix, add them all up and generate the output. And this will generate an output which could be used for regression, or we might want to compare it with a threshold and make a classification. Anyway, this is basically a forward pass through the network. That's what it's called, a forward pass through the network. So the data coming in in this case on the left and going out at the right, generating a prediction. So this is, forward pass, recognition mode if you're running it as a classifier. Now, when we're actually training a network, we have to also do something else. First of all, we have to generate the output corresponding to the input, or I should say we have to generate the prediction corresponding to the input vector given the weights we've got, and then we have to compare what the output prediction is with what we actually want the output to be. So this only works when you've got labeled data, of course, so we need labeled data. This is a supervised learning algorithm, so for each input data set, each vector, we've got a corresponding target, and we need to compare those two. Then what we do is we generate this error, so we're going to take the difference between target and predicted output, or predicted value from the network, generate an error, and then propagate the error the other way in order to change the weights. And this is the backward pass. So imagine we've got this 2D example with 2D data, two-dimensional data, so basically the rows are the dimensions of the data, and in this case we've got n data vector samples, so we've got vectors basically, each column represents a data sample. In order to deal with getting the bias term into the weight matrix and making the algebra much more simple, what we need to do is make sure that we append the data so we can actually do calculations in this matrix form. So we append basically the data vectors, so we now end up with a three-dimensional vector per sample, but the same number of samples. So basically then we end up with a weight matrix which has also been appended with the bias term. In this case it's a nice simple system. This is just a 1/3 system that we end up with. And of course, because we're going to be training this network, we actually need, for every single input vector, we need a corresponding target that we want the network to actually get or generate. So this is also going to be, in this case with a single output, it's going to be a one-dimensional vector per data sample, and there are as many data samples as there are samples coming in on X, right? So for every vector we've got a corresponding target. In this case it's just a 1/n matrix. Now for a single output linear network, we're just going to say the output is just going to be the net term. So we're just calling the net term the linear part of a neural network. So let's think about, for a single input vector, we generate a single output. So for pattern I, the output's going to be OI, and we can look at calculating the squared error for that particular pattern as being the target value for that pattern that we're given, take away our predicted output for that value, squared. So EI is just basically TI minus OI squared. And again, we square it because we don't want to use just the signed error. If we did that, when we start averaging or adding up error across vast numbers of samples, it can be that obviously the positive and the negative parts are going to cancel out. We're just going to put a factor half in front of this just to make the calculations a little bit cleaner when we differentiate. You don't need it at all, it's just convention in this particular example. So obviously that's just the error for one particular sample I. Generally what we need to do is say what's the total error across the entire data set, so we've got to sum EI up over all data points, so we put a sum in front of EI. When we actually implement that in MATLAB, obviously what we'll do is we'll just do the thing as matrix operations, and we don't have to do that, we'll do it basically with a matrix multiplication. So let's substitute in EI into this expression for total error, and we just substitute in the half, which we're taking outside the sum because it's a constant, and let's sum across all data samples 1 to n of ti minus oi squared. Okay, and that's just information for you so you can see what it all means. Now we want to do gradient descent in order to minimize the error in terms of the weights. So in other words, we want to find the weights which give the minimum error across the entire data set, just like we did in linear regression. So what do we need to calculate? Well, we need to calculate dE dW, right? And don't forget, E is going to be a scalar value and W is going to be our weight matrix in general, right? And if we've got K features in the input data, so in this case we're saying we have K features x1, x2 plus this augmented 1, so it will be 3. We have to have the corresponding number of values in the weight matrix as well, right? So the weight matrix, if we had a dimension of input vector k, right, and we've got k elements in the column, then we have to have k weight values in the row of, in this case, of the single dimensional case weight matrix. Therefore, when we differentiate the error, which is a scalar in this case, with respect to the weights, we end up with a result which is the same dimensionality as the weight matrix. So in this case we've got a 1 by k dE dW matrix. So let's write down the error for pattern I, or for data point I, as EI equals half TI minus OI squared. What we're going to do now is we're going to calculate the differential, and to do that we want to split it up using the chain rule. So let's start looking at this. We see it's a function of a function. There's a TI OI part here, and then that's squared. So the first function is going to be the TI minus OI, and then the second one's going to be the EI equals a half UI squared. There should be an I on there. So let's now calculate the error gradient with respect to the weights. So what we care about is dEI dW, right, for this sample error, which is dDW of half UI squared. So we're just substituting this expression into our derivative formula, and just basically then we're going to just use the chain rule in order to evaluate it. So dEI dW is dEI dUI dUI dW, and we see that that's the case because you can cancel out the UIs. And it's easy to calculate these two terms. So dEI dUI. So look at UI here. Look at EI here. Got to differentiate that with respect to UI, not U, because that's a missing off there. So you end up with a half times 2UI, right? So the half cancels out, and we end up with dEI dUI equals UI. And then we pop back in what we had in terms of TI and OI, right? So that's that term sorted out. Then we've got to differentiate UI with respect to W. That's the second term here with respect to W. First of all, we note that TI really hasn't got anything to do with W at all, so it's constant, so that disappears. But now we've got to differentiate OI with respect to with the weight matrix, and the output does depend on the weights, right? So we can't say that, just because there isn't a W term here, OI does actually depend on the weights. So let's just write it down first of all as dOI dW, the differential of OI. And of course it's negative here because we've got a minus sign here. So we have a minus sign here. So the reason we can't just, we have to calculate this term is because OI equals WX, or WXI in this case. So it's just a sample value. So we have to calculate the derivative of this term here. We can't just assume it's constant, because it's not constant. It actually depends on W. So substituting as much as we can already, then we see that we've got dEI dW. That's this term here. Is built up of the chain rule terms. So the UI term multiplied by the du dW term here. So the first bit comes to the first differential dEI dUI, gives us this TI minus OI term here. Second one gives us the minus dOI dW term. So minus dOI dW. And now we've got to sort out what the differential of dOI dW is. But we know for a linear network, like I said, that OI equals WXI. So W is the weight matrix, XI is a single vector for that data point I. And we know that DDW of WX equals X transpose, right? We did that in one of the first lectures. So what you see is it's quite easy to calculate this derivative, dOI dW. It's simply going to be XI transposed, right? Therefore, looking at our expression for DEI dW, we just substitute in our XI transpose term, right? That's what this is here. In it goes, and we end up with our DEI dW, which is minus TI minus OI multiplied by XI transposed, right? And that gives us the gradient of the error with respect to the weight vector. In this case, it's a vector. So, actually, we want to care about the error now across the entire data set, so we need to sum up this error. Don't forget, we can't just basically just do it sample by sample. Well, you can do it sample by sample when you're doing updates, but let's look at the error across the entire data set. So this is going to be the sum of all the square errors. So it's going to be substituting in the value. It's going to be the sum across all data points of TI minus OI squared, and we've put the scaling factor outside. And if we want the derivative of E tot with respect to W, what we can do is we can simply just look at this first term and actually move the derivative inside the sum. So it's the sum across all data samples of DEI dW, which we've already got, the DEI dW. It's then the sum across all samples of TI minus OI XI transposed. And using this expression, we can actually calculate the error gradient over the entire data set, right? And actually, obviously there are i's in this, but we could actually do this and this calculate. We can do this calculation vectorized if you just take the i's off, and then this is then the vector of output targets. This is then the vector of predicted outputs, and then this is the vector, or sorry, I should say the matrix of all the data points across the entire data set. So let's think about pseudocode now that can actually solve our problem. And what we want to do is we've got the error. We can calculate the error gradient with respect to W. If we know that we've got the error gradient with respect to W, what we can do is we can update W iteratively, right? So starting off, we randomly initialize our weight matrix W to realistic values. Important thing to note is here they've got to be something which is, you know, as close as possible to what we think the solution might be. So they're going to be generally very tiny values. Because it's an iterative algorithm, you wouldn't want to put big values in there if the values that it's going to finally find, and of course you don't know what they are, but if you put 20 billion or something, it's going to take an awfully long time to actually move down if the value should be about 1, right? So you have to think about that. We're going to use augmented data X in this particular example, and the way we're going to carry on then, after initializing W, we're going to have an iterative loop that's going to first of all generate the prediction. In fact, we're doing it across the entire data set here, right? W is the weight matrix and X is all the data, so O is now an output vector of all predictions across all samples. We then calculate the error gradient with respect to W, and again we can do that vectorized, so it's actually doing it across the entire data set. So we calculate all the outputs minus all the predicted outputs and do a matrix multiplication with all the data transposed. And then what we need to do is we need to update the weight matrix W, or the weight vector in this case, by taking a little bit off it in the direction of the gradient. So we say W equals minus alpha dE dW. And in fact, just looking at this term, you can see, right, that the gradient of the error has got to be the same dimensionality as W, otherwise you couldn't do this. Alpha is just a very tiny number, usually, which is the learning rate, and it shows well, it basically tells the system how far to move each step down the gradient, and it shouldn't be too big. Right at the end, we've got some kind of termination condition. Could be looking at how small the error's got. It could also be that you've done so many iterations. Same kind of thing we were doing with linear regression by gradient descent. Let's now have a little think about the sizes of some of these vectors, just to make it completely clear. This is something which is a useful exercise when you're first implementing these things in MATLAB, because MATLAB will complain if you don't get the dimensionality the right way round. First of all, if the output, this is a 2-output linear network we're going to think about now, is going to be equal to Wx, where we've got simple matrix multiplication. In this particular case, x is going to be, in fact this is just a single value, a single sample, it's going to be a 3×1 vector, right? So we've got 2 data points on a bias term. The weight matrix is going to be a 2×3, so don't forget the inner size has got to be, the number of columns in this has got to be the same as the number of rows, otherwise you can't multiply them. But we see also that we've got 2 outputs in this system, right? So we've got, so we have to have 2 rows of weights. This first row of weights at the top corresponding to the first output, and the second row of weights correspond to the second output. And if we look at the sizes of these things, right, the output then is going to be always rows by columns. It's 2×1, and that's equal to dimensionality of the weight matrix, which is 2 rows by 3. And the x is basically 3 rows by 1. So you can see immediately the output is going to be 2×3, because those are the outside dimensions of the product. Similarly, the target's going to be a 2×1. It's got to be the same size as the output, right? So you've got 2 outputs here, net 1 and net 2. Then you need 2 targets. So what we need to calculate now is going to be the gradient with respect to w. And we know that dEdW is going to be minus t minus target minus output multiplied by the transpose of the data vector x. In this particular case, dEdW is going to be the same dimensionality as w, right? So it's got to be 2×3. And again, you can intuitively see that it's got to be, because we're going to be taking this value off w, and if this isn't the same dimensionality as what you're taking it away from, you can't do the calculation. So that's one way of checking. In this particular case, we've got 2 outputs, so the output is 2×1, so t is 2×1, o is 2×1, and in this case we've got a single data vector, so this is basically a 1×3, right? So we've got 1 1×3, because it's basically 3×1 transposed, right? Multiplication is basically matrix multiplication, so it's doing this basically weighted sum kind of calculation for us. Okay. So what we then do is we're going to update w by moving down towards a minimum error, right? So w goes to w take away scaling factor alpha multiplied by dEdW. Again, like I said, weight matrix is 2×3. Alpha is just a scaling factor, so that's actually a 1×1. So in actual fact, that's going to scale every element in dEdW, right? So that's a 2×3, but because we've got an alpha in front of it, it will let you scale with a 1×1. And this is then actually element-wise multiplication, because you're scaling each individual value of the dEdW by the alpha.